Hey AP Chem, welcome to today's discussion of molecular polarity. We have done a lot of discussion about bonding so far. So you guys have talked about ionic bonding, you've talked about covalent bonding, we've talked about drawing a Lewis structure, we've talked about the bond lengths, we've talked about drawing resonance structures and formal charge, and Vesper shapes even. And so today we're going to be talking about molecular polarity. Now, molecular polarity is probably the last thing that we have to do with bonding that's kind of tricky. And I would say that it is one of those things that practice makes perfect when we are talking about polarity. And so it's going to be really important that you go through your practice problems to get things cleared up, because the more you do them, the more you visualize them and the better things go. So we're going to revisit covalent bonds for just a second, and then we'll talk about how that leads into polarity. So one of the things that we've talked about with covalent bonds is that a covalent bond is an overlapping of two electron shells for two atoms, and they share those electrons. But what we did not talk about is how those electrons are not always equally shared in a covalent bond. Much like all things in life, sometimes someone gets a little bit more, someone gets a little bit less, and not everybody's necessarily always happy about it, but that's the way things go. And the same thing happens in a chemical bond. Sometimes the two electrons that are shared between those overlapping orbitals don't end up being shared equally. So what happens is one element has the electrons closer to them than the other element does. And depending on how the custody of those elements' electrons work out, they may lead to what is called a polar bond. And so what a polar bond is, it's a bond between two elements where the electron density, or the position of the shared electrons essentially, accumulates on one side of the bond. So what you'll see is that you'll see the electrons hanging around one element substantially more than they are around the other element. And because electrons are negative, you end up getting differences in actual charge. Now, it's not a fully charged ion like it is in an ionic bond, but what ends up happening is that you get a partial negative end where your electrons hang out, and a partial positive end where your electrons haven't hung out. And that's because your electrons are negative. So if you have more electrons hanging down by one element than another, they take on a character that's kind of like a less than impressive ion. And then the other side is less than impressive positive ion. What happens is, in an ionic bond, the pull is just so strong that they separate into a full charge, and a covalent one is like, well, we just couldn't quite commit to pulling apart, so we're just sharing unevenly. And that polarity of the bond comes from differences in electronegativity. We talked about electronegativity a little bit when we talked about periodic trends, and how, excuse me, and how the electronegativity determines how equally those things are shared. And so if we come back to this chart here, we'll see that, again, fluorine has the highest electronegativity value, and francium down here at the bottom left-hand corner has the lowest electronegativity. And the electronegativity is just a number that represents how strongly an element pulls its electrons towards itself in a bond. So what ends up happening, and I need you to understand that this is I call it a squishy scale. And what I mean by that is the range on here kind of can get pushed a little bit, especially once we start talking about ionic bonds. So the way that it works is that you have to actually physically look at a bond and calculate the difference between it. And you have to do this for every different bond that you have in a Lewis structure. So if you have a Lewis structure where you are calculating the electronegativity difference and you have three different bonds, you need to do three different calculations to figure out each of the bonds' polarities. So the way that it works is that you look at the table here, and then you find the two electronegativity values. So if we see here, this first example is C and H. So you have a Lewis structure that has a C and an H in it. We find C has an electronegativity of 2.5. We find H has an electronegativity value of 2.1. I always pick the bigger number minus the smaller number. There's nothing kind of more complicated than that. And then you find the difference between them. And generally, the way that it works is that if there's a difference of 0.4 or less, so kind of this division line here, you end up with two elements that are sharing their electrons pretty evenly. And so we consider them nonpolar. What that means is that there isn't a really electron dense area on one side of the bond and an electron poor area on the other side. They're shared pretty nicely. But anywhere between a 1.8 and a 0.4, this kind of middle chunk that you see here, that is the region where they are still technically shared electrons, but they are shared unevenly. And the way that it works is that the bigger the difference in electronegativity is, the more polar that bond gets. And so if we have something that's got a polarity difference or an electronegativity difference of 0.6, that's going to be a much less polar bond than something that has a polarity difference of 1.2. So understand it's kind of like a sliding scale. And then in the neighborhood of 1.8 or 1.9, if you start to get differences that are that big, you are going to get an ionic bond. There are exceptions to this, okay? We're going to see one in the next slide, but understand that if we get up into that range, we have a very uneven sharing of our elements, electrons, and we have almost an ionic bond in that case. And in the case of metals and nonmetals, most of them have such a big difference that that's why they end up with the actual ions forming instead of the shared bond. So it has to do with that difference in electronegativity. So this is hydrofluoric acid HF. And if we go back and look at H and F, H is a 2.1 and the F is a 4.0. So if we take a 4.0 minus a 2.1, we get a difference of 1.9. And yes, I know I literally just told you that 1.8 is there. HF is honestly the top end of the differences that you're going to see while still having a covalent bond between the two elements. So it is covalent, but I can tell you that they are very unevenly shared. And this picture here, I think, does a really nice job of showing you that. So the colors here represent electron-rich areas and electron-poor areas. And we're going to kind of visualize those a little later with our examples using those colors. Okay, so what happens is the closer to the reddish color you see, that is a more electron-rich area. And in the case of the HF bond, that is because F has the higher electronegativity. So a higher electronegativity element always draws the electrons towards it. So in our bond here, the electrons hang out much more next to the, much more next to the F than it does the H. And this blue side here indicates that H is electron poor. What we do to show that is we draw in this little, looks like a little squiggly sign here. It's kind of like an 8 that you got just like too tired to finish. That is the lowercase Greek letter delta. So if you think of the capital letter delta, you've probably seen it. It's a triangle. This is the lowercase version of that. Or it's like a D with a fancy little hat off the top of it. And that stands for a partial charge. And so instead of this being like an ionic bond where we have a negative and a positive, what we have is these little symbols here, which stands for a partially positive or a partially negative. And again, the element with the higher electronegativity value always gets the partial negative in a polar bond. If you don't have a polar bond, and I can't emphasize this to you enough, you do not have the separation of charges. So in the case of like carbon and hydrogen, how they have a difference of 0.4, they do not get the symbols here, okay? And you'll see that in some of the examples. So why we're talking about polar bonds is that polar bonds give rise to polar molecules. And honestly, molecular polarity is probably one of the biggest factors in taking a look at how molecules behave on a macro level. So if I mix this with this, why don't they mix together? It probably has to do with their polarity, and it's a huge, huge component of actual physical chemistry that we do. When we talk about a polar molecule, it's the same idea, but what ends up happening is if you think about the whole molecule, there is an uneven distribution of electron charges. So in a polar bond, it's one positive side and one negative side. In a polar molecule, it's differences in charges on the whole molecule. So we look at the whole thing instead of just one individual bond, okay? When you have this polar molecule, it causes something called a dipole moment. And a dipole moment is just a fancy word for saying it's polar. So if you say which one has like the greater dipole moment or which one of these exhibits a dipole moment, it's just a fancy way of saying, is this polar? Which one's more polar? So dipole moment and polar are kind of used. Dipole moment is just like the fancy way to say polar. Okay, now, and this is why we did VSEPR shapes first. The VSEPR shape is what leads us to having the polar or nonpolar molecules in addition to the bonds. So there's kind of two factors there. You need polar bonds, and then the VSEPR shape is going to be an indicator for that too. And symmetry is going to be key in determining whether something is polar or nonpolar. And symmetry in VSEPR terms is different than what you might think of math symmetry. So we'll kind of go through that. Okay, so determining molecular polarity. The first thing you need to do is you need to successfully draw your Lewis structure. Once you successfully draw your Lewis structure, then you need to figure out the polarity of all the bonds in the molecule. Okay, if you have one type of bond, it's easy peasy, but if you have different types of bonds in there, it takes a little while. So again, first thing, Lewis structure. Second thing is going to be your bond polarity. Third thing then is going to be taking those things into consideration with the VSEPR shape. And the way that it works is that if you have all nonpolar bonds, so you go through the whole process and you find that there are nonpolar bonds throughout the entire thing, you have a nonpolar molecule. Like you just can't have a polar molecule without polar bonds. So that's the first thing. Big things that you need to remember with this, C to H is nonpolar. And an element to itself is nonpolar. Those are the big ones. You do not get the electronegativity table on the AP exam. So you need to keep it locked up here that C to H is nonpolar. Okay? Then, all identical polar bonds around your central atom and no unshared pairs means that you have a non-polar molecule. And this is where symmetry is going to play an important part. So when I talk about a molecule being symmetric, I talk about it not having any unshared pairs around its central atom. So these are going to be shapes like linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. So if I have all the same polar bonds around my central atom and I have no dots on the center, I'm going to have a nonpolar molecule. And you're going to say to yourself, that seems really strange, but we'll get into that when we get into the examples. If you have all identical polar bonds and then unshared pairs on your molecule in the center, you are going to have a polar molecule. Okay. And then lastly, if you have a mix of polar and nonpolar bonds, you are going to have a polar molecule as well. Okay. So we're going to be going through some examples next. I want you to, when we go through them, one, I'm going to give you the title of it, or not the title, the formula, and then you are going to draw me the Lewis structure. Then you are going to get the partial negatives and positives figured out, and then you're going to try the polarity, and we will walk through those as we go along together, okay? So give those a try, be patient. It takes some practice to kind of get the hang of it, and then we will kind of wrap up bonding in our next lesson, all right? Good luck.